Welcome to our comprehensive crash course on algorithms. This video was created by a team with backgrounds from IITs, top UK universities, and other leading global institutions. Because we genuinely love building things and explaining how they work. If you find this content helpful, please hit that subscribe button and ring the notification bell so you don't miss any of our upcoming computer science tutorials. Your support helps us create more in-depth educational content just like this. Have you ever used Google Search or called a taxi online and wondered how it chose results or calculates routes so quickly? The secret to that mind-bending speed is something called algorithms. In today's crash course, we'll learn what algorithms are, why they matter, and how we measure their efficiency using a powerful tool known as Big O notation. So, what is an algorithm? At its simplest, it's a set of instructions to accomplish a task or solve a problem. Think of it as a recipe for computers. For instance, sorting a list of numbers, there's an algorithm for that. Finding the shortest route on Google Maps, that's an algorithm too. Even sending messages over the internet or encoding videos depends on algorithms working in the background. But here's the catch. Not all algorithms are created equal. Some are lightning fast, others are painfully slow. And some use far more memory than necessary. So, how do we compare them objectively? That's where complexity analysis comes in. Big O notation is how we characterize an algorithm's performance as input size increases. We focus on two main aspects: time complexity, how long it takes, and space complexity, how much memory it uses. Let's work through some common examples. O of 1, constant time, takes the same time regardless of input size. Think of accessing an array element by index, fast and predictable. O of log n, logarithmic time, time grows slowly as input size increases. Binary search exemplifies this. Each step cuts the dataset in half. O of n, linear time. Time grows proportionally with input size. A good example is searching through an array for a specific number. O of n log n, linear arithmetic time. Better than quadratic, but slower than linear. Heap sort and merge sort fall into this category, ideal for sorting large datasets. O of n squared, quadratic time. Performance degrades drastically as input increases. Insertion sort and bubble sort exhibit this complexity, not ideal for large data. And yes, it gets worse. Algorithms with complexities of O of 2 to the n, or O of n factorial, exist. But let's save those for more advanced discussions. The key takeaway? Lower time complexity generally means better performance. When analyzing algorithms, we don't just look at one scenario. Instead, we consider three cases. Best case, when everything goes perfectly. For example, in linear search, the target is the first element. Average case, what happens most often across many runs. This gives us realistic performance estimates. Worst case? The worst case scenario. We typically focus on this to ensure predictable performance. Consider quicksort as an example. Its best and average cases are O of n log n, but the worst case can degrade to O of n squared. In contrast, merge sort consistently delivers O of n log n performance. Depending on your application, predictability might be as important as raw speed. Want your algorithm to run faster? One approach is to use additional memory to store pre-computed results. This is the time-space trade-off. A classic example is calculating Fibonacci numbers. The naive, recursive approach is exponentially slow. However, if we store previously computed results in an array, a technique called memoization, we can reduce it to linear time, at the cost of additional memory. In practice, you'll often face such decisions. Do you need better performance or less memory usage? Understanding these trade-offs helps you make informed design choices. Let's recap what we've covered. We explored what algorithms are, why they matter, and how big O notation helps us measure their efficiency. We examined different complexity classes, from constant time through quadratic and beyond. We learned the importance of considering best, average, and worst cases, and how time and space often compete with each other. Next, we'll explore the fascinating world of sorting algorithms. We'll start with simple techniques and progress to the advanced methods that power everything from spreadsheets to enterprise data systems. Let's dive in. Sorting is arguably one of the most fundamental operations in computer science. From displaying search results, to organizing game-high scores, to preparing data for efficient retrieval, sorting is central to making programs faster and smarter. You might not even realize it, but almost every advanced computer system relies on sorted data at some point. Let's begin with basic sorting techniques. While they may be slow, they'll help you understand how sorting works at its core. Bubble sort is probably the most simplest sorting algorithm and often the first one taught to beginners. The concept is straightforward. Repeatedly pass through the list, checking if each pair of adjacent elements is in the correct order. If not, swap them. After each pass, the largest unsorted element bubbles up to its correct position at the end of the array. You continue this until the array is sorted. And optimization is to exit early if no swaps occur during a complete pass, indicating the list is already sorted. While bubble sort is easy to implement and visualize, it becomes very inefficient as input size grows. Next, we have selection sort. This algorithm divides the array into two regions, sorted and unsorted. Initially, the sorted region is empty, and the unsorted region contains the entire list. At each step, the algorithm finds the smallest element in the unsorted region and places it at the end of the sorted region by swapping it with the first element of the unsorted region. Selection sort performs fewer swaps than bubble sort, which can be advantageous when writing to memory is expensive. However, it still makes many comparisons and, like bubble sort, has O of n squared time complexity, regardless of the initial order. While it minimizes swaps, it remains too slow for large inputs. Then there's insertion sort, which often performs better than other basic algorithms for small or nearly sorted lists. The algorithm works similarly to sorting a hand of playing cards. It builds the sorted list one element at a time by taking each new element, comparing it with previously sorted elements, shifting larger values to the right, and inserting the new element in its correct position. When the input list is nearly sorted, minimal shifting is needed, and insertion sort operates in nearly linear time. In the worst case, such as when the list is in reverse order, its efficiency drops to O of n squared, but it remains practical for small or nearly sorted datasets. Now, let's examine the algorithms commonly used in production systems. These efficient sorting algorithms are significantly faster, typically running in O of log n time, making them practical for large datasets. First up is merge sort. Merge sort exemplifies the divide and conquer strategy. The concept is elegant. Split the array into two halves. Recursively sort each half. Then merge the sorted halves into one sorted array. The merging process compares the smallest elements from each half and builds a new array with elements in the correct order. This recursive splitting and merging continues until the entire array is sorted. One of merge sort's greatest strengths is its consistency. It always runs in O of n log n time, whether the input is already sorted, reverse sorted, or completely random. It's also a stable sort, preserving the relative order of equal elements, which is crucial for applications like sorting database records with multiple fields. The main drawback is that merge sort requires additional space for temporary arrays during merging. This makes it less suitable for memory-constrained environments, but ideal for external sorting or linked lists where consistent performance and stability are priorities. Quicksort is another highly efficient sorting algorithm, often faster than merge sort in practice. It also uses divide and conquer but takes a different approach. It selects a pivot element from the array and partitions the other elements into two subarrays according to whether they're less than or greater than the pivot. After partitioning, we have two smaller subarrays that can be recursively sorted using the same process. Quicksort's efficiency comes from being in place. It doesn't require extra space like merge sort. Its best case and average case time complexity is O of n log n. But poor pivot selection, such as always choosing the first element in an already sorted array, can degrade performance to O of n squared. This can be mitigated using smart pivot selection strategies like choosing a random element or the median of 3 method. One limitation is that quicksort isn't stable. It doesn't preserve the order of equal elements. Despite this, its speed and memory efficiency make it the default choice in many programming libraries, including C++ and Java. Finally, we have heap sort. This algorithm leverages a binary heap data structure, typically a max heap to sort elements. First, it builds a max heap from the input data, ensuring the largest element is at the root. Then it repeatedly extracts the root, the maximum element, places it at the end of the array, and reheapifies the remaining elements. This process continues until the array is sorted. Like merge sort and quicksort, heap sort runs O of n log n time for all cases. One advantage is that it doesn't require extra memory. It sorts the array in place. However, it's not a stable sort, and in practice, it's slightly slower than quicksort due to the overhead of maintaining the heap priority. That said, heap sort is valuable when memory is limited or when you need guaranteed O of n log n performance, such as in priority queue implementations. Choosing the right sorting algorithm depends entirely on your specific requirements. For small datasets or educational purposes, bubble sort, selection sort, and insertion sort are adequate. They're simple to implement and understand, though inefficient for large inputs. For large datasets requiring stable and predictable performance, merge sort is the safe choice with guaranteed O of n log n time and stability. If you need maximum speed and stability isn't required, quicksort typically offers the best practical performance. When memory is limited and you need in-place sorting with guaranteed performance, heap sort is your best option. Each algorithm makes different trade-offs between speed, memory usage, and stability. To summarize, we started with simple sorting algorithms: bubble sort, selection sort, and insertion sort. These introduced fundamental concepts like comparisons and swaps, though they're impractical for large datasets. Then we advanced to production-ready algorithms: merge sort, quicksort, and heap sort. These demonstrated how recursion, pivoting, and heap data structures can dramatically improve performance. Along the way, we touched on core computer science concepts, including time and space complexity, in-place operations, and algorithm stability. With sorting mastered, we can now proceed to searching, starting with binary search and exploring powerful optimization techniques. Now that we've mastered sorting the data, the next challenge is searching within it efficiently. Searching permeates every aspect of computing, from finding contacts in your phone to querying databases to web searches. Efficient searching dramatically improves both speed and user experience. In this section, we'll explore two fundamental techniques: linear search, which works on any data, and binary search, which is much faster but requires sorted data. We'll also introduce an advanced technique called binary search on the answer, commonly used in competitive programming. Let's start with linear search, the most straightforward search algorithm. It examines each element in the list sequentially until it finds the larger target or reaches the end. It's simple and doesn't require sorted data. Here's how it looks in code. Loop through the array, check if each element matches the target, and return the index if found. Return -1 if the element isn't present. The worst case time complexity is O of n, meaning it might need to examine every element. However, in the best case where the target is at the beginning, it's O of 1. It requires constant space and works on arrays linked lists, or any iterable structure. While inefficient for large datasets, linear search is useful when data is small, unsorted, or when the target is likely near the beginning. Next is binary search, a much faster algorithm that only works on sorted data. Instead of checking each element, it repeatedly halves the search space. It starts by comparing the middle element with the target. If they match, we're done. If the target is smaller, search the left half. If larger, search the right half. Repeat until the element is found or the range is exhausted. We maintain low and high pointers and calculate the middle index in each iteration. We adjust the pointers based on the comparison and continue. Binary search has O of log n time complexity, making it far more efficient for large lists. The best case is still O of 1, and it can be implemented with constant space using iteration. However, it has limitations. It only works on sorted data and isn't efficient for non-random access structures like linked lists. Binary search can be adapted for various applications: finding the first or last occurrence of a value, or finding the smallest element greater than the target. These variations frequently appear in technical interviews. Now, let's explore a more advanced technique: binary search on the answer. Here, we're not searching an array, we're searching a range of possible answers. The key insight is that if you can test whether an answer is valid and the solution space is monotonic, once valid, always valid for larger, smaller values, you can use a binary search. For example, to find the smallest x where x squared greater than 30, instead of testing every number from 1 to 30, we binary search the range. We make a guess, square it, and check if it meets our requirements. If it does, we save it as a potential answer and try smaller values. If not, we try larger ones. This powerful technique appears in problems involving resource allocation, task scheduling, or finding optimal thresholds. You need two things: a way to validate a guess and a monotonic search space. To recap, linear search is simple and flexible but slow. Binary search is much faster but requires sorted data. Up next, we'll explore the fascinating world of graphs, structures that model networks, maps, and countless real-world relationships. Graphs are everywhere. Social networks, roadmaps, computer networks, airline routes, and even neural networks. A graph consists of nodes or vertices connected by edges. These edges can be undirected, like Facebook friendships, directed, like Twitter follows, or weighted, like distance between cities. Graphs help us model complex relationships and solve real-world problems. Finding the shortest route on Google Maps, detecting cycles and systems, or determining if two people are connected in a network. In this section, we'll explore how graphs are represented and how to traverse them using fundamental algorithms. There are two primary ways to represent graphs: adjacency matrix and adjacency list. An adjacency matrix uses a 2D array to represent connections. If matrix ij equals 1, there's an edge from node I to node j. This approach is simple to implement, but requires O to the n squared space, making it impractical for sparse graphs. An adjacency list, on the other hand, stores a list of neighbors for each node. For instance, node 0 might have nodes 1 and 2 as neighbors. This representation is space efficient and ideal for traversal operations. It's the most common representation in real-world applications. Breadth First Search (BFS) is a fundamental graph traversal algorithm that explores nodes level by level. Starting from a source node, it visits all immediate neighbors before moving to nodes further away. This makes it perfect for finding shortest paths in unweighted graphs, as it always explores closer nodes first. BFS uses a queue to manage exploration. We begin by adding the starting node to the queue and marking it as visited. While the queue isn't empty, we remove the front node, process it, and add its unvisited neighbors to the queue. This ensures we visit nodes level by level, processing all nodes at distance k before visiting nodes at distance k plus 1. One primary application of BFS is finding shortest paths in unweighted graphs. Useful for maze solving or social network analysis where each connection has equal weight. It's also used for level order traversal in trees, where we process nodes level by level. Another application is determining whether a graph is bipartite. By alternating colors while traversing, we can check if a two-coloring is possible, an indicator of bipartiteness. However, BFS isn't suitable for weighted graphs since it doesn't consider edge weights. For those scenarios, algorithms like Dijkstra's are more appropriate. In summary, BFS is simple yet powerful, perfect for exploring graphs by distance from the source, finding shortest paths in unweighted graphs, and performing systematic traversals. Depth-first search, DFS, is another fundamental graph traversal algorithm. But while BFS explores breadth first, DFS explores depth first. Starting from a node, it follows one path as far as possible before backtracking. Think of it like exploring a maze. Follow a path until you hit a dead end, then backtrack and try another route. DFS is typically implemented using recursion or a stack. We start at the initial node, mark it as visited, and recursively visit all unvisited neighbors. This naturally handles backtracking. When a node has no unvisited neighbors, we automatically return to the previous node. One primary application of DFS is cycle deletion. By tracking visited nodes and the current path, DFS can identify whether a graph contains cycles. In directed graphs, DFS enables topological sorting, ordering nodes so that all dependencies come before dependents. DFS also helps find connected components, groups of nodes that can reach each other. This is valuable for clustering problems and social network analysis. In maze solving, while DFS might not find the shortest path, it guarantees finding a path if one exists. However, DFS isn't ideal for shortest path problems in unweighted graphs, since it doesn't prioritize closer nodes like BFS does. It will find a path, but not necessarily the optimal one. In summary, DFS excels at exploring graph structures deeply. It's simple to implement, naturally supports backtracking, and is essential for problems involving connectivity, cycles, and dependencies. While BFS works for unweighted graphs, weighted edges require Dijkstra's algorithm. It efficiently finds the shortest path from a source node to all other nodes in graphs with non-negative weights, using a priority queue, typically implemented as a MIN heap. The algorithm maintains a distance array initialized to infinity for all nodes except the source, which is 0. At each step, it selects the unvisited node with minimum distance, updates its neighbors' distances if a shorter path is found, and repeats until all reachable nodes are processed. Dijkstra's algorithm is reliable and optimal for most real-world applications, but it doesn't work with negative edge weights. In those cases, you'll need the Bellman-Ford algorithm. To recap, graph model complex relationships using nodes and edges. Adjacency lists efficiently represent sparse graphs. BFS finds shortest paths in unweighted graphs through level-by-level exploration. DFS excels at deep traversal, cycle detection, and connectivity problems. Dijkstra's algorithm handles shortest paths in weighted graphs with non-negative weights. Graphs are among the most versatile tools in algorithmic problem solving, enabling us to model relationships, optimize routes, and analyze networks. Next, we'll explore dynamic programming, an elegant technique that trades memory for time by caching results. It's a game changer for problems with overlapping subproblems and optimal substructure. Let's begin. Imagine you're solving a complex problem, and halfway through, you realize you've already solved this subproblem before. Wouldn't it be efficient to reuse that result instead of recalculating it? That's the essence of dynamic programming, DP, a powerful technique that excels when problems have overlapping subproblems and optimal substructure. DP saves computation time by storing and reusing intermediate results. Let's explore the core concepts. Overlapping subproblems means a problem can be broken into smaller parts that appear multiple times. Consider computing Fibonacci numbers. The same smaller values appear repeatedly in naive recursive calculations. Optimal substructure means that solving subproblems optimally leads to an optimal solution for the larger problem. If we get the smaller pieces right, we can confidently build the complete solution. These two properties form the foundation of DP. There are two main approaches to implementing DP. First is memoization, which uses recursion when caching. When solving a subproblem, we store the result. When the same subproblem appears again, we return the cached result. It's intuitive and follows natural recursive patterns, but may be slower due to recursion overhead. Second is tabulation, where we solve the smallest subproblems first and iteratively build up to the final answer using a table or array. This approach avoids recursion entirely, making it generally more efficient. While slightly harder to implement initially, it offers better performance and clarity once mastered. Let's solve a classic problem, finding the nth Fibonacci number using the relation f of n equals f of n minus 1 plus f of n minus 2. The naive recursion solution recalculates many values and has O of 2n squared time complexity, becoming impractical for large inputs. By using memoization or tabulation to store previously computed Fibonacci values, we reduce time complexity to O of n. This simple example powerfully demonstrates how DP dramatically improves efficiency when subproblems overlap. Now let's tackle the coin change problem. Given coin denominations and a target amount, find the minimum number of coins needed to make that amount. Using tabulation, we create an array where each index represents the minimum coins needed for that value. We iterate through each coin denomination, updating our table based on previously computed values, building our answer from the ground up. This algorithm runs in O of n times amount, time, and demonstrates how solving small subproblems optimally leads to the overall optimal solution. It's a classic example of DP applied to optimization problems. For our final example, consider the longest common subsequence. Given two strings, find the length of the longest sequence appearing in both, not necessarily contiguous. We use a 2D DP table to compare characters from both strings. When characters match, we increment the count from the diagonal cell. When they don't match, we take the maximum from adjacent cells. The bottom right cells gives us the LCS length. This problem has widespread applications in DNA sequencing, diff tools, and text similarity measurements. Another powerful demonstration of DP solving real-world problems. In summary, dynamic programming is essential for problems with overlapping subproblems and optimal substructure. The two main approaches, memoization and tabulation, provide flexible problem-solving strategies. Classic DP problems include Fibonacci numbers, coin change, and longest common subsequence. Next, we'll explore greedy algorithms, where we make locally optimal choices hoping to achieve a globally optimal solution. Greedy algorithms make the locally optimal choice at each step, hoping these choices lead to globally optimal solutions. They're typically simpler and faster than dynamic programming, but don't always work unless the problem has specific properties. When they do work, they provide elegant and efficient solutions. For a greedy approach to succeed, two properties must hold. The greedy choice property means we can reach the global optimum by making locally optimal choices. Optimal substructure means the problem solution contains optimal solutions to its subproblems. When both properties exist, greedy algorithms often achieve O of n log n or even O of n time complexity. However, many problems that seem greedy-friendly actually aren't, so you must verify correctness, often by comparing against a dynamic programming solution. Let's start with the activity selection problem. Given activities with start and end times, select the maximum number of non-overlapping activities. The greedy choice is to always pick the activity that ends earliest, leaving maximum room for future activities. By sorting activities by end time and selecting non-overlapping ones, we achieve an optimal solution in O of n log n time. Next, consider the fractional knapsack. We have items with weights and values, and a knapsack with limited capacity. We want to maximize total value. Since we can take fractions of items, the greedy approach sorts items by value-to-weight ratio and takes as much as possible from the highest ratio items first. This yields an optimal solution. Note that this doesn't work for the O1 knapsack problem where items must be taken whole. That requires dynamic programming. Our final example is Huffman coding, used in data compression. It builds an optimal prefix-free code by repeatedly combining the two least frequent characters. This greedy strategy constructs a binary tree that minimizes the total encoded message length. Greedy algorithms are fast, simple, and elegant, but only when the problem structure allows it. Real-world applications include activity selection and scheduling, fractional knapsack optimization, Huffman coding for compression, minimum spanning trees using prims or Kruskal's algorithms. Let's move on to divide and conquer, a strategy that breaks problems into smaller, manageable pieces. Divide and conquer is a powerful algorithmic paradigm where we break a problem into smaller subproblems, solve them independently, and combine their solutions. It works best when problems have optimal substructure, meaning the complete solution can be built from solutions to smaller parts. Let's examine some classic examples. Merge sort perfectly exemplifies divide and conquer. Divide. Split the array into two halves repeatedly until each subarray contains one element. Step 2. Conquer. Sort each half, trivial for signal elements, and combine. Merge the sorted halves into a fully sorted array. This approach achieves O of n log n time complexity and maintains stability. Binary search is another excellent example. Given a sorted array and a target value, compare with the middle element. If smaller, search the left half. If larger, search the right half. This halves the search space with each operation, achieving O of log n performance. Other notable divide and conquer applications include finding maximum-minimum elements efficiently, matrix multiplication, like Strawson's algorithm, finding the closest pair of points in computational geometry, fast Fourier transform for signal processing. Divide and conquer works best when recursion simplifies the problem and the combination step can be performed efficiently. Congratulations! You've explored the fundamental pillars of algorithm design: sorting, searching, graphs, dynamic programming, greedy methods, and divide and conquer. When approaching algorithmic problems, remember to understand the problems thoroughly, identify patterns, and always consider time and space complexity. Practice regularly on platforms like LeetCode, Codeforces, and HackerRank. Start with basic patterns, master them, and gradually build your intuition. Finally, remember, algorithms aren't just about coding. They're about thinking clearly and solving problems effectively. Keep practicing, keep learning, and happy coding. Thanks for watching.